Our next presenter is Dr. Andrew Brainard. He is a senior research scientist with the Upstate Freshwater Institute. He focuses on how freshwater ecosystems are impacted by human activities, including invasive species, climate change, and emerging contaminants. The title of his talk this morning is "Change is Going to Come, but Will We Know? The Value of Long-Term Lake Monitoring." Welcome, Andrew.
Thank you, Anne. You've made it to the last talk of the morning, so big hand for the other presenters. Those talks were excellent. Yeah. If I do my job, I think a lot of what I'm going to talk about will sort of synthesize and summarize some of what we heard in the three previous talks. So I'm here this morning to really give an overview and kind of make the case as to why long-term monitoring of lakes matters. And I thought, given that this is a sort of a different forum than what I'm used to as a scientist and presenting results, I thought maybe, well, I'll hit them over the head at the beginning with the key message, the key take home, right at the jump. And I'm thinking about, putting the presentation together. How am I going to do that? And then I could sit up here and wave my hands and say, yeah, long-term monitoring matters. Listen to me, listen to me. But that's not overly convincing. So I'm going to try to do something. So if you'll indulge me for a moment, I'm going to try to make you feel why long-term monitoring of our lakes matters. So if you're so inclined, at the risk of putting you to sleep at the beginning here, if you would like to, close your eyes and imagine that you're along the shoreline of your favorite lake, wherever that lake may be. It's early evening. You're there with your friends and loved ones. The birds are singing. The sun is setting. There's a cool breeze. And as far as you're concerned, in that moment, that point in time, there's no place better to be. That lake is as best as it's ever been. Okay. Now, what if I told you that just underneath the water, the fish populations are in decline, fish are disappearing. There's a new invasive species that was introduced the previous year that is now established, starting to spread in your lake, and that the water quality of your lake is slowly deteriorating. How would you know? Change is inevitable. It's the constant in all of our lives. It's no different with our lakes that we love. Change is going to happen. The only way to know and document that change is through monitoring. Okay. So that's my presentation. Thank you, everybody. Thank you for your attention. No, but in all seriousness, that's the take home. If you get nothing else out of this, I hope that you felt that the need that for long-term monitoring is real. And the only way that we're going to document change is through looking for it and making observations. All right, so here's what you're actually in for. So I'll talk a little bit about long-term monitoring, what it is, how we use it, and then kind of give you, sort of base cases as in terms of why it matters. A couple, looking at lakes across New York State, looking at trends and different trophic indicators, touching on the elephant in the room, climate change. And then I'll end by using Owasco Lake as in the model that was done for Owasco Lake to show how we use those long-term monitoring data in an applied sense to model. Okay. All right, so what is long-term? What do we mean when we say long-term? It probably means something different to everybody, right? So brainstorming, what does long-term mean to me? What could it mean to you all? And I kind of came up with a certain criteria, or decisions. What does long-term mean to us? The first one is not very satisfying. An infamous quote, when you see it, right? Well, that doesn't mean a whole lot, right? What I see when I look at a data is different than what you see, and what's long-term to me is different than you. The second point up here is that in certain situations, from a statistical standpoint, if we want to detect trends or change over time, we need a certain amount of data in order to have statistical power in order to detect trends. So there's a mathematical basis for what we mean by long-term. And most importantly, I think it ultimately depends, it's context dependent. It depends on the question you're asking, what your specific objective is to understand what is long-term to you, okay? So I'd like to drive this point home in the previous talk that I gave on this topic. I think this is a nice way to sort of synthesize. Instead of me just speaking it to you and giving you some bullet points, I'm going to demonstrate to you, I think, what we mean by long-term and the value of it here. So this is just hypothetical graph. This is a parameter XYZ collected over a 3-month time period. Okay. So is this long-term? Probably not, right? If we were going to say, okay, we now understand the system based on what that data is suggesting, not very convincing. If we make management decisions based on that data, we're likely to be wrong in terms of what we're going to do to address that. Okay. So that's 3 months, not long-term. This is a year. Again, that same parameter. Those first 3 months are there on that figure. So the first 3 months now we're plotted over a year. Now we have a little bit more sense of what's going on in that system, what that parameter is doing over time. And we're more informed than we were when it was, the 3 months of data. Okay. So that's 1 year, not bad. 5 years. Again, the red box is that 1 year time period. Now we have 5 years of data with that parameter over time. Now we can see, okay, relatively constant over time. There seems to be some peaks and valleys, probably a seasonal effect of what that parameter is doing. Now I think we would say, yeah, we have an understanding of what this parameter is up to over that 5-year period. 10 years of data. Now we have a decade. Okay. This is where the insightful information comes from. So in that first 5 years of that parameter, pretty constant. There's a seasonal pattern, peaks and valleys, but pretty constant over time within that first 5 years. After year 5, that parameter has changed, right? So then in the preceding 5 years, something happened along that 10-year time period in between after 5 years and corresponding to the 10-year where something's happened. This is where long-term monitoring and the data that comes from it is extremely useful. Now we know and have a better understanding of what that is operating that system and what we can do to manage it potentially. All right. So why do we care? Why do we care about long-term monitoring and the data that comes from it? So patterns, again, like that example. When we have a long enough record of our long-term monitoring, we can see patterns emerge. All right. We ultimately, I would argue, need that information in order to make informed decisions based on science, right? Scientific discovery is an interesting one. So a lot of times monitoring programs will be set up, long-term programs, essentially just, to collect the data. We have a basic interest in a certain lake area. We go out and we collect data, maybe for assessment purposes. But on the back end, having all that information allows for discovery of other phenomena with that data, right? So think like, I'll present some CSLAP data and I'll talk about what that is, but that's basically a volunteer assessment program, collects data. But the benefit that comes from that is that as researchers, stakeholders, interested folks, we can take that data to try to address other questions. And then of course we can use all that data and ultimately need that data to develop models and ecological forecasting, those type of applications. So again, figure on the bottom left, 3 months of data, we're likely to make bad informed decisions and lead to bad outcomes. More data we have, the better shape we are, that we can manage systems and understand what's going on. Okay. So here's where the sort of potpourri of examples comes in. And we're going to look at trends in trophic indicators across the state using CSLAP data. I mentioned that long-term monitoring data is important, it's critical, and we are very fortunate in the fact that we are in the era of big data, right? Especially in the environmental field. So if you think about all the acronyms that are out there, NEON, LTER, GLEON, GLOSS, it's an acronym soup, but essentially there's a lot of monitoring programs that are at our fingertips. Think about the USGS gauges that Dr. Halfman mentioned at the Owasco Inlet. And the number of those gauges that are across the country, it's almost too much to think about and have at our fingertips, but we do have it. So let's use it. And in New York State, we are extremely fortunate that we have the CSLAP program, the Citizens Statewide Lake Assessment Program, another acronym, unfortunately, but CSLAP, as we love and call it. So this program, again, so fortunate that DEC and their wisdom and got together with NYSFOLA back in the mid 1980s and developed this program. So super insightful back in the day, and that carries through to today. Essentially, if you're not familiar with it, it's a trained volunteer program where the volunteers go out in their home lake, collect data over the growing season, and have that data analyzed. So the goals of the program really are threefold: collect the data, identify problems, and use that data to educate. So the numbers here are a little old, but back in 2021, there were 164 lakes in the CSLAP program in that given year. I think since then, the number has increased, but a lot of lakes participate annually. And it's a truly unique data set in terms of limnology right here in New York State. All right. The cool thing about the CSLAP program is that it provides, again, this consistent long-term monitoring, so we can look at trends, we can look at different things. It also produces reports. So I'm going to speak to this specific to CSLAP, but this is also applicable to any long-term monitoring program. So these annual reports, the annual data that's collected, is really like a chapter in a book, right? It's not the whole book. If you were to look at 1 year data, you're reading a chapter, but in totality is where the book comes from. And I'll steal a quote from Dave Matthews, who UFI director. The annual reports or the annual data that gets added to a long-term monitoring data set is like the rest areas. They have to happen, but they're not memorable. It's a trip along the way, a stop along the way. Okay, so even as Dr. Happen was showing his data, right? Every year that he's added to his long-term record is like a rest stop, but in totality is where the value comes in. All right, so using CSLAP data, we're going to look at 3 trophic indicators. So total phosphorus, chlorophyll, and Secchi depth. And again, we're going to pop around the state just looking at a few examples. So this is Lake Moraine. This is in Madison County near Hamilton, so east of here. It's a mesotrophic lake, meaning it's semi-productive, right? It's not oligotrophic. It's not as low productivity. It's not eutrophic, where it's highly productive. Mesotrophic, sort of in the middle. And in terms of total phosphorus over a 34-year period with the CSLAP data, we see no change in total phosphorus over that time period, okay? We see a decrease in chlorophyll A, so essentially the amount of algae in the water column decreases on an annual basis, and an increase in Secchi depth, and those are sort of correlated. If you have less algae, tend to have greater water clarity, okay? So I point out here in the red circles, these annual rest stops along the way. Taken out of context, if we had, a few years of data before and after those points, we wouldn't see this overall long-term trend. So just, again, driving the point home that those outliers, in the context of the long-term record, really don't tell the whole story. It's the long-term record that matters. Okay, here's Black Lake. This is up in the North Country, a eutrophic lake, so a productive lake. Also, no change in total phosphorus over a 32-year period in this case. Similar decrease in chlorophyll and an increase in Secchi depth. So in this case with Black Lake, like with Lake Moraine, looks like things from a nutrient standpoint, total phosphorus standpoint, no real change. Better in this case, better, quote unquote, from a chlorophyll and Secchi depth standpoint. And again, those outliers. This is Ballston Lake in the Capital Region. A little different story here. So this is a eutrophic lake. Over a 29-year period when this analysis was conducted, we do see, in fact, an increase in total phosphorus over that time period, corresponding to an increase in chlorophyll. So, and these are just 3 trophic state indicators, but increased nutrients in terms of phosphorus, driving increased growth in the algae, chlorophyll, and a corresponding decrease in our water clarity, Secchi depth. Okay, so again, that's just an example of how we're using long-term data to gain knowledge in terms of lakes and the patterns that we're seeing. So this is a kind of a summary of that whole analysis where, using 100 or so CSLAP lakes, just looking at trends across the state. So in terms of total phosphorus, what the analysis is suggesting is that about 2/3 of the lakes that were included didn't have any change at all, no trend, no increase, no decrease in total phosphorus concentrations on an annual basis. About a quarter of them had an increase. So a quarter of those lakes increased total phosphorus, a significant trend, and about 12% had a decrease. Okay. Chlorophyll and Sucky are kind of the same story. About half of those lakes did not have any detectable change, no trend over that time period in chlorophyll A or Sucky depth. And you can see the breakdown there. So in a nutshell, what analysis is sort of suggesting, again, using that long-term monitoring data that is so critical, that there's really no, give or take on average across the state and the lakes that were included, there's really no generable change in trophic state indicators. Now, I'll hit this point again, but every lake is different, right? So this is just a generalizable pattern across these trophic state indicators in New York State lakes. If you live on one of those lakes that's changing, you probably would say, yeah, this is important, right? So context. All right, so climate change trends. So we heard this morning from Mark a lot of really important information as it relates to what New York State's up to with climate change. I'm going to bring you into the water and show you some of what we see in terms of lakes and climate change with some examples and some long-term data. Before we do that, just a little limnology 101 for a moment, if you'll allow me to. So what's the big deal? Why do we care about climate change in lakes? Well, this is just one example, but I'm going to show you how climate change theoretically is going to impact our lakes. Okay. So you can see that's a blue blob. Please stretch your imagination to think that's a lake. Okay. Surface on top, bottom water on the bottom. We have our sun. This is under base conditions, typical lake that stratifies in the spring to summer period. Okay. So sun shining, it's springtime, air temperatures warming up. That is warming up our surface waters. Okay. The bottom waters are still relatively colder compared to the surface waters. So there's now a temperature difference, and the warmer, less dense waters on top, the colder, higher density waters on the bottom. And when stratification occurs, those layers of water do not mix. Okay. So that's lake stratification in a nutshell in a typical dimictic lake, meaning 2 turnover events a year. And we can actually measure the amount of energy required to have those 2 masses of water mix. Okay, so we call that stratification strength. All right, now we're under a climate change. Now our air temperatures are warmer. So it's hotter, and the air translates to warmer surface temperatures in the springtime into summer. Okay, perhaps earlier in the season than before on average. So now we have warmer, less dense water on top, colder, higher density water on the bottom, and the strength, the amount of energy required to mix those 2 layers of water now is greater, right? Under hypothetical climate change impact on lakes. Okay. And again, that's just one element to how climate change may impact our lakes, but I think one that we can kind of get our arms around. So again, can we actually assess this and see this in terms of looking at surface water temperatures in our lakes over time? So that's what we'll look at. So this is, again, CSLAP data. This is a handful of lakes that have a really long-term record in CSLAP. And what you're seeing is as data is getting added, it's surface water temperatures plotted against Julian day, essentially just the day of the year in the summertime period. And going back from the 80s, it's going to go through to about 2020, if I let it go that far. But pick your favorite lake on here, watch it add data over time. And what you'll see is that there is, in fact, our lakes in New York State are getting warmer in terms of surface temperature. Okay, so it is occurring. We can document it with long-term data. And in totality, again, with the CSAP lakes and the lakes included in this analysis, what the data is suggesting is that our surface waters in our lakes are warming by about 0.6 degrees centigrade per decade. So again, not a huge increase over the long period. If you think of 0.6 degrees centigrade as, daily fluctuations were well beyond that. But again, over that long-term period, over a 10-year period, that it certainly is occurring. All right, so that's an annual period, annual average. This is now monthly increases in surface temperatures. Okay, so we're looking at June, summer period, June, July, August, and September, with just a subset of these lakes. Again, with a long-term record going back to the in some cases, the late 1980s. So what we see here, so earlier in the summertime, the June period, we see that 0.6 degree Celsius increase per decade. The middle summer months, we see a slightly higher increase per decade of 0.7 degrees C. And the interesting point is in September, so the later month, an even greater increase in surface water temperatures of our lakes, 1.1 per decade, okay? So is climate change having an effect on thermal structure of lakes? I think pretty compelling evidence that it is occurring here in New York. All right, so maybe we'll look at some lakes in the central New York. If you're familiar with these lakes, Tully Lake, Crooked Lake, Song Lake, and Little York, just north of Portland, south of Syracuse. And I'm going to show you a different story here with these kettle lakes and try to explain to you why this may be happening. So this is Little York Lake, again, looking at those monthly averages over time. Doesn't seem to be much occurring in Little York Lake over this time period, right? Only in August, there's a slight squint your eyes and see an increase in surface water trend. And if we look at the other four lakes, not a whole lot going on. And in fact, in Song Lake, it looks, based on this period and this data, sea slab data, there may be an increase or decrease, excuse me, in surface water temperatures over a time period. So does this suggest to you that climate change isn't having an effect on surface water temperatures in central New York? I would argue it is not. Look at the X scale. So this is from 2012 to 2021, about a decade, right? And I previously showed you that in the lakes with a really long-term period, it's about a 0.6 degrees increase per decade, okay? So I think what's happening, and I would make the argument that the record, even though it's a decade for these lakes in central New York, small kettle lakes, not long enough to see a trend yet, right? Once the Little York Lake folks, Song Lake, once they have 30 years of data, surface water temperature data, perhaps we will see that effect, okay? That's me going like, what's going on? All right, here's another interesting case. And again, these are sort of case studies, and we'll get to some applications here in a moment. But so we talked about strength of stratification, right? The more energy theoretically under a climate change scenario, warmer surface, colder, deeper, more energy required to mix. So we can actually measure that, right? By how many days in a given year that a lake is stratified. So this is from Onondaga Lake in Syracuse, where UFI has had a long-term monitoring program dating back to the 1980s. So 40 plus years of monitoring Onondaga Lake. And we've had a buoy out there since the inception. And what you can't see is that underneath that buoy, there's a pulley system with a YSI multi-probe on there that 2 times a day, it'll go and take a temperature reading every meter, generally between April and October of every year. Okay. So using that data and looking at the trend of how many days a year is Onondaga Lake stratified, and there is a significant trend. Now, granted, that's a lot of scatter, right? So there's other things going on, as we can probably all imagine. Onondaga Lake's a complex system, different inputs from a water treatment plant. That's warm water being introduced. So there's a lot of dynamics, urban lake. But in general, the number of days that Onondaga Lake is stratified has increased over roughly 40-year period. And it's about 1 week per decade. Okay, so we're talking decadal scales, right? If we were to go out and say, okay, well, I want to look at the impacts of climate change on Lake X, I think what we're sort of suggesting now is, okay, we need to have a monitoring program that's decades in length in order to really find anything meaningful within that data. Okay. All right, climate change isn't just temperature, it's also precipitation. So this is a little nod to the precip that we heard a lot about earlier this morning. So this is the NOAA station here in Auburn. Again, long-term record, 1950s, there's gaps in it, that's okay. If you squint your eyes, you probably would tell me that that's not a significant trend, but I didn't put statistics on here for a reason. If you look at the 1950 to 1970 roughly period, again, squint your eyes, looks like total precipitation in inches over the summer period is lower relative to roughly 2010 to 20, those points generally above that trend line. So there is, and if you look at the scale, again, I don't want to get into details here, but the scale is roughly 10 inches per summer total to now up to 20. Okay, so it is increasing. We can all agree on that. And we know, based on some of the work that John has done and has presented this morning, that more rain in Auburn correlates well with more inflow volume to Owasco Lake. So climate change is impacting the hydrology of our lakes, not just the temperature, but hydrology, right? Okay. So that's really just a spattering, a potpourri, if you will, of how we use long-term monitoring to look at different nutrient trophic states, climate change, learn a lot about our lakes based on long-term monitoring. Now I'm going to introduce how we actually use that data and apply it, or can apply it, to things like models here in Owasco Lake. So I'm sure you're all intimately familiar with the Owasco Lake model. John talked about the SWAT model for the 9-element plan. I'm going to talk a little bit about the in-lake model, which is a C equal W2 model. I'm not going to bore you with model details. Okay, I'm just going to basically tell you it happened, show you how we did it in a really quick slide, and then show you what the model tells us. All right. I'm not a modeler either, so it'd be way over my head if I talked about model logistics. But essentially, the Owasco Lake model is an in-lake water quality model, simulates summer conditions, using the 9EP for management actions, trying to evaluate why cyanobacteria HABs may be happening, and run scenarios to make management recommendations. Okay. These models, in this case, this Owasco model was pretty, it's on the higher end of the complexity. So I just want to show from a process standpoint how the data is used. So this is a hydrothermal element of that model. And then if you look at the black points within those figures, and then look at the black points are the actual data. That's the empirical data measured through a long-term monitoring program. The blue line is what the model is used in simulating the empirical data. Okay, so I'm just showing you that the data that is collected through a long-term monitoring program has applied use, in this case, through the hydrothermal model for Owasco Lake. Okay, we didn't have that data. We didn't have the black circles. We wouldn't be anywhere near as good a fit with our model data, right? Our simulations wouldn't be, we had no confidence whatsoever if we tried to model this from a mechanistic standpoint. All right. Okay, that's enough model logistics that I'm going to talk about. I'm going to show you some cool results. So again, looking through the lens of climate change with the in-lake model for Owasco, this is looking at, again, that increased duration of stratification. So what's on the left is the base case. This is I think it's a 19-year model simulation. So that's the base case of what the model's spitting out based on what we know today. The two panels to the right are a different climate change scenario, RCP 8.5, in 2025, 2050 and 2080. Okay. So pretty compelling evidence from the model suggesting that in those two endpoints, 2050 and 2080, under that climate change scenario, that there's going to be increased stratification duration. So Owasco Lake will be stratified longer than what is currently occurring. Okay. Stratification strength. So we also talked about and showed you that silly little diagram where the more energy is required to mix those two layers of water when surface water temperatures are warmer, colder or cold bottom water temperatures, it takes a lot more energy to mix it. Okay, so again, this is the black line, if you can squint and see the color differentiation. Black line is base case. The blue and the red are those two different endpoints with that single climate change scenario. So suggesting that not only is Owasco Lake going to be stratified longer, the strength of that stratification, the density difference between those two layers of water is going to increase as well. And finally, surface water temperatures. So I hopefully demonstrated to you that surface water temperatures are increasing across the state in our lakes. No difference here with what the model is suggesting for Owasco Lake, that in 2050 and 2080, under that climate change scenario, surface temperatures are going to be higher than they are now. Okay. I threw that green line on there. And again, I think we're on pretty solid ground to say that cyanobacteria favor warmer water temperatures, particularly surface water temperatures. So that's a 25 degrees threshold that above that line favors cyanobacteria. They like it warm. Sounds like they also like it cold too, but let's not scratch our heads all at once. Okay, so this is my sort of final summation of this application use of the Owasco Lake data in the model. So we can also use that once we have the model set up, informed by long-term monitoring data, simulated, confidence in it, we can then run scenarios to try to understand if this, then that, based on what the model can tell us, okay? So this is looking at chlorophyll concentrations and total phosphorus concentrations. Again, the current conditions that the model's spitting out gives a certain 3.2 concentration of chlorophyll, 8.1 concentration of TP, okay? We then have these scenario runs where we say, okay, 10% reduction in total phosphorus, 20, 30% reduction. And the model suggests that with those percent reductions of inputs, loads to the Owasco Lake, that we'd see a decline in both chlorophyll and phosphorus. Now this is where it gets fun, so stay with me. The next two scenarios, we have a 30% reduction, so similar to scenario 3, 30% reduction of TP, but all that TP is particulate, okay? So coming in on sediment, it's particulate form. The fifth scenario, 30% reduction, so same as scenario 3, but all that phosphorus is dissolved, okay? So it's now dissolved. It's more readily available to phytoplankton for grow, okay, to grow. And if you look at that, we have 30% reduction, 2.8. If we have all particulate, remove all the particulate out of there, it doesn't do us any good based on what the model is suggesting. But if we have 30% that's in dissolved form, it looks a lot better in terms of chlorophyll and phosphorus, okay? So I would argue, based on the model results here, and I think elsewhere, that the form of phosphorus that we're trying to reduce is critically important, okay? All right, now, here's where I'm gonna knock your socks off, I think. Scenario 6, same as scenario 3, okay? 30% reduction in total phosphorus. But scenario 6, we have a 2 degrees Celsius increase in air temperature. So we're trying to evaluate climate change, essentially. All right, so if you look at those two scenarios, you say, oh, well, 30% reduction in TP gets us 2.8, gets us 6.8 total phosphorus. And about the same if we have a 2% increase with the same amount of phosphorus reduced, okay? I'm gonna show you why the model says that would be an incorrect assumption. All right, so again, here's that table, those two arrows pointing to those two different scenarios. That's just that data, same data plotted with chlorophyll and TP, all right? Now I'm gonna show you how the phytoplankton assemblage changes under those two scenarios, okay? And particularly looking at the cyanobacteria. So 30% reduction in TP, we have a concentration of cyanobacteria and a percent of cyanobacteria, the total phytoplankton down here, pretty comparable with the other scenarios. We have a 30% reduction in TP, so we're still reducing total phosphorus loads, but we tick the temperature up, 2 degrees C. Look at how that composition changed, okay? So it's suggesting that with climate change, we're likely to see an increase in cyanobacteria, right? All right, I'm going to conclude with a couple take-home points here. So I hope I've convinced you that long-term monitoring is critically important for many reasons. We use it to look at patterns, we use it to model, we use it to learn more, we use, to model with tools, to use scenarios so we can, learn more and see if we're right based on what we know today. And it helps us make scientifically informed decisions. That's paramount. With the CSLAP data, no real obvious trends in trophic condition, right, across that broad region, New York State, with all those lakes. But New York State lakes are becoming warmer at the surface, some more rapidly than others. And then I'll leave you with this final thought that in science, we always try to find the generalizable patterns, right? We almost crave it. We have to generalize everything. So what I mean by that is what works in this lake, our understanding, the evidence suggesting it's got to work everywhere else. We need it to, crave it. But that's not always the case, right? I think that's a critically important point, that every lake has its own story. what's true or what we think is true for a lake in the Adirondacks isn't going to necessarily mean that's the same. It's going to be in the Finger Lakes, Long Island, for a lake in Utah. So every lake has its own story. And I think we avoid those nuances to our peril at times. So leave you with that take home point. I'm happy to answer any questions.
Thank you, Andrew. That was great. Got a couple of questions remotely. One is kind of long, but I'm sure you're familiar with it. Basically, it's speaking to the DEC's push to reduce C-SLAP monitoring from 8 samples down to 4 over 2 years. So the question is, how do you feel that might impact long-term data? And given that, would you recommend a continuance of field data over 8 times?
I'm not going to take a position necessarily. I'll just say that continuing monitoring is important, right? 4 is better than none. Yep. Who asked that question?
Can you speak to the potential of internal phosphorus loading and associated HAB production as it relates to climate change and the increased duration of lake stratification in Owasco?
Yeah, this gets really complex. So if our lakes are stratified longer, and bear with me because I may get over my skis here, but our lakes are stratified for longer, right? That means there's the greater potential for anoxic conditions in the hypolimnium, that lower, denser layer, which means there's a greater likelihood that there could be internal nutrient release from the sediment through redox chemistry. But if our lakes are stratified for longer, that means they turn over later, which means that slug of nutrients coming from the bottom, the hypolimnion, may now mismatch when we would typically have phytoplankton growing. Okay. That's a theoretical thought. That's not, I don't have any evidence to back that up. And the other interesting thing to think about is lakes that stratify and then mix and stratify and mix. So they're polymictic over the course of a season, right? They're stratifying, potentially releasing nutrients in the sediment, and that's just getting mixed up over the growing season. With climate change, which may be a beneficial thing, those lakes may then stratify throughout the whole season. So that continuing release of nutrients over the growing season isn't happening any longer because our surface waters are warmer and that strength to stratify or strength of mix is greater. So again, I don't have any evidence to back that up. That's just a hypothetical exercise to think about what maybe happened.
I have one more from the remote group here. With the projection of water temps increasing over time, if we continue to use fertilizers and pesticides to the degree that we are today, will the warmer water temps increase the negative impacts in our lake?
Not sure. So this question always comes up. I'm probably not going to answer this question directly, but we're all often asked, what do we do? What should we do, right? Related to HABs or any kind of lake management, water quality issue. And it's kind of a weekly conversation that we have with many different folks. And I'm going to be flippant for a moment, but strictly in terms of water quality, the best thing that we could do is everybody get out of the watershed, right? Everybody leave, get the humans out of there. That's not possible. Realize that. So that's not a should, right? Question then becomes, what can we do? Okay. And from that perspective, if you boil that down, I think Dr. Halfman's data kind of suggests this too, that again, strictly in terms of water quality, from a loading standpoint, the best land use land cover is forested. Okay. So again, should we get rid of all of ag? Absolutely not. We all need to eat. It's a huge economic driver of this region, the Finger Lakes. So that's not on the table. All right. So again, what can we do? We can, at the simplest form, try to make our watersheds act more like forested landscapes. Well, how to do that? I don't know. But that, I think, is the crux of the question. What can we do? That's what we can do.
For the water sampling, would it, this is Philip Joya from Auburn, for the water sampling, would be more beneficial to target the sampling after heavy rain events?
Yeah, it's always tough, right? It's you have all the investment, you set aside resources to do it, the people, the manpower, people power, excuse me. And then you try your best to do it. We try our best to do it. We sometimes succeed, we sometimes don't. It's just the nature of monitoring. Yeah. Yep. You do your best to try to capture all the variability. Sometimes you're successful at doing it. Sometimes you're not. But in general, you want to get all the variability in your system that you possibly can in your monitoring program. Yep. Highs and lows, right? Yep.
Thank you.
All right. Thank you.
Well, we heard an awful lot here today, a lot to digest and to take in. Big messages. We work together. We look at ways that we can solve these issues, protect the drinking water source here for our community, yet still enjoy the lake for recreational purposes. This event today has been taped. It will be on YouTube under the Owasco Watershed Lake Association account. And always feel free to reach out to members of AULA if you have questions to go into more detail of what we have had presented today. Our goal is to continue to educate and to build awareness to allow better capacity as we identify working opportunities here to improve the lake. So thank you so much for coming here to the 2023 Bob Brower Symposium, The Effects of Climate Change on Owasco Lake. It's much appreciated.